In this video, I'm going to explain about how to expand log 1 plus x as an infinite series. So when we look any log function, so whatever inside the log will be always positive. So log function is defined for positive numbers. So here we have taken the function fx equal to log 1 plus x. So this is defined only if this is greater than 0. So we have here 1 plus x should be greater than 0. So if we find from here, we get x is greater than minus 1. So log function is, for this log function is defined only when x is greater than minus 1. So we'll try to find fx. We have taken here fx log as 1 plus x. So you differentiate this, we get f dash x, which is 1 by 1 plus x. Again, if you differentiate this, we get 0 plus 1. 0 plus 1 is nothing but 1, so we get 1 by 1 plus x. This can be written as 1 plus x to the power minus 1. So if we differentiate again this, we get here minus 1, 1 plus x to the power minus 2. So we get here minus 2. So in the similar manner, we can expand this again. We get minus 1 to the power minus 2, 1 plus x to the power minus 3. So if we differentiate the nth time here, so we can see that when it is 3, we have minus 1, minus 2. So minus 1, we have 2 minus. So when it is n, we'll have n minus 1. So we have here minus 1, minus 2. We can say 1, 2 here. So when it is 3, it is 2. So when it is n, it will be n minus 1. So we have minus 1, minus 2 till minus n minus 1. And when it is 3, here we have 3. So if it is n, it will be nothing but minus n. So we get 1 plus x to the power minus n. So this, if I take the minus, so we have how many minus here? We have n minus. So we have we have n minus 1 minus. So minus 1 to the power n minus 1. And if we write 1 into 2 into 3 into 4 till n minus 1 is nothing but n minus 1 factorial. So we get here n minus 1 factorial. And this is minus n, so we can bring down. So we get 1 plus x to the power n. So we try to find fn0. So fn0 is nothing but minus 1 to the power n minus 1 factorial. So this is your fn0. Now we try to find the remainder in Lagrange form. So here we are taking both Lagrange form as well as Cauchy form. So we take the remainder in Lagrange form. So we have here xn by n factorial fn theta x. So xn by n factorial, we get here is this theta, here we put as theta x. So we get minus 1 to the power n minus 1 factorial 1 plus theta x. So 1 plus theta x to the power n. So here is n factorial, so here is n minus 1. So n factorial can be written as n into n minus 1 factorial. So n minus 1 factorial, n minus 1 factorial will get cancelled. So we are getting minus 1 to the power n minus 1 by n. So this x to the power n, I'm taking this and this I'm taking together. So we get here x by 1 plus theta x to the power n, where 0 is less than theta is less than 1. Then we try to write the remainder in Cauchy form. So this is the remainder in Cauchy form. X to the power n, n minus 1 factorial 1 minus theta to the power n minus 1 fn theta x. So xn by n minus 1 factorial 1 minus theta to the power n minus 1. So in place of here, so we have this already, we have find fn x. So you put here theta x. So we get here minus 1 to the power n minus 1 factorial 1 plus theta x to the power n. So we get here 1 plus theta x to the power n. So n minus 1 factorial, n minus 1 factorial will be cancelled. So we get here x to the power n minus this minus 1 to the power n minus 1. I'm writing here x to the power n. And from here, if I break into two parts, so we can, if I write here 1 plus theta x into 1 plus theta x to the power n minus 1 is same as 1 plus theta x to the power n. So I'm breaking in that way. So we get here 1 by 1 plus theta x. So I take this and this together. So we get 1 minus theta divided by 1 plus theta x to the power n minus 1. Now I'll try to write the Maclaurin theorem I'll try to write this log function as a finite series. I'll try to write the Maclaurin theorem for finite series of log functions. So if I write this, I get here as fx equal to f of 0 plus x f dash 0 plus x squared by 2 factorial f double dash 0 plus x cubed by 3 factorial f triple dash 0 plus so on, plus x to the power n factorial fn theta x. So this is the Maclaurin theorem in Lagrange form of remainder. So we have this x minus x squared by 2, x plus x cubed by 3 plus so on, minus 1 to the power n minus 1 xn by n, 1 plus theta x to the power n, where 0 is less than theta is less than 1. Now we have seen that already we have seen that this log function is defined for x greater than -1. It is not defined for x below x less than -1, so it is defined only for x greater than -1. So for first of all we try to prove between -1 and 1. So we are adapting for we'll try to prove for x lying between -1 and 1. So we are for this we'll assume the Cauchy form of remainder. So we try to show the Cauchy form of remainder tends to 0 as n tends to infinity. So we can see that this quantity will always tends to 0 as n tends to infinity, since the value is lying between -1 and 1. So since the value is lying between -1 and 1, so any value which is lying between -1 and 1 will be something 1 by 2, 1 by 3, 1 by 4, so on. So if we take x to the power n, so this will be nothing but if I take x to be 1 by 2, so we get 2 to the power n. So as n tends to infinity, this quantity will become bigger and bigger, and this will approach to 0. Since the value of x, okay, so the value of x is lying between -1 and 1, this quantity is tending to 0. It's not that for any value for any value of x this quantity will tends to 0. It's not true that, but since the value is lying between 1 and -1 and 1, the value of x will be in fractions, so this will approach to 0 as n tends to infinity. So that's why we have here xn tends to 0 as n tends to infinity, and this quantity 1 by 1 plus theta x is finite, and we have that 1 minus theta by this is always less than 1. So this is less than 1, so if you take to the power n, so it will be bounded. To the power n minus 1 is bounded. So we have this is your Cauchy remainder. Now this tends to 0, and this is finite, this is bounded, so everything is finite here. So this tends to 0 means a whole thing will tends to 0. So we get that this tends to 0 as n tends to infinity in mode of x less than 1. So that mode of less than 1. Now we try to prove when x equal to 1 it converges or not. So for doing that, we try to assume the Cauchy remainder form. So here we have when x equal to 1, okay, when x equal to 1 we'll take the Lagrange form of remainder. We have what here? Rn equal to -1 to the power n minus 1 by n, 1 plus theta x to the power n, 1 plus theta x to the power n. We are putting x equal to 1, so we get this. Now this quantity will tends to 0 because here is n, so this quantity whole thing will tends to 0 as n tends to infinity. So when x equal to 1 also the series converges. So that's why we have that log 1 plus x equal to x minus half x squared, 1 by 3 x cubed minus plus -1 to the power n minus 1 x to the power n by n plus so on, which converges for all the values which is lying between -1 is less than x is less than equal to 1. Thank you.